Let's look at counting significant digits in data. We use data to make decisions and calculations. If other people give us data, how do we know which zeros is significant and which are just placeholders? For example, we are told an iron atom's diameter is 0.0000156 meters. There are 10 leading placeholding zeros. The 1, the 5, and the 6 show precision. We can use scientific notation to get rid of placeholding zeros by writing 1.56 times 10 to the negative 10th. In a second example, the world has 7.5 billion people. The 7 and the 5 show precision. There are 8 trailing placeholding zeros that tell us nothing about precision. Again, we can use scientific notation because scientific notation never uses placeholding zeros, and we would write 7.5 times 10 to the 9th people. In science, we use significant figure rules to figure out which zeros are significant. We say placeholder zeros are insignificant because they don't indicate precision. Trailing zeros are insignificant unless there's a decimal point. So our first value, 45 centimeters, has two significant digits, the 4 and the 5. 450 centimeters has only two significant digits because that trailing zero just indicates a place. It's a placeholding zero. We could have 451, we could have 448. 45,000 also only has two significant digits because we have two trailing zeros that don't tell us anything about precision. However, if we add a decimal point, as we have right here, now we have four significant digits because that decimal point tells us that we know all of the trailing zeros. We have a decimal point again right here. 4500.0 has 5 significant digits because we have that decimal point. Without the decimal point, the trailing zeros are just placeholders. Placeholding zeros disappear in scientific notation. So we've taken the previous values and rewritten them in scientific notation. We have two significant figures, so we're going to have two significant figures shown in the scientific notation. We have two significant figures here, two significant figures in the scientific notation. Two significant figures here, two significant figures in the scientific notation. When we put in that decimal point, now we have four significant figures, so our scientific notation will show four significant figures. We have 5 significant figures. Our scientific notation shows 5 significant figures. Leading zeros are always going to be insignificant. If we have no leading zero, then we have 3 significant figures. We rewrite it in scientific notation as 1.23 times 10 to the first. Scientific notation is useful to show the number of significant digits. The second example, we have a leading zero. So I've underlined the significant digits. That first zero is just a placeholder. If we have 0.1230, I'm underlining the significant digits. We have 4 significant digits. 0.000123 has 3 significant digits because the leading zeros are just placeholders. And then our last number, we've got 12.30, or 1230 point. We've got 4 significant digits. And notice in each case in our scientific notation, that front number, the coefficient, shows all the significant digits. Let's look at practicing counting significant figure rules. Remember, leading zeros are always insignificant. They're just placeholders. We're going to use a decimal point to decide if trailing zeros are insignificant. We'll decide which zeros are placeholders. For the first value, we have 2 placeholding zeros. For the second value, our two leading zeros are just placeholders. Third value, we have 4 trailing zeros with no decimal points. All the crossed out zeros are just placeholders. For the fourth value, we've got 4 leading zeros. We would say that all of them are insignificant. They're just placeholders. And then our last one, we should have all of the zeros are significant because of the decimal point. So if we count the number of significant figures, we have 3 significant figures in the first value, 3 significant figures in the second, 3 significant figures in the third, 2 in the fourth, and 4 in the last. There's one last rule. Exact counts and exact conversion factors, we say they have an infinite number of significant digits. For example, I have exactly 2 children. It's not 1.998 or 2.04. They're exactly 2. So I treat that like there's an infinite number of significant zeros. There are exactly 12 eggs in a dozen. So I would treat that like it's 12.000000 on forever. So in summary, when we're counting significant figures, trailing zeros are significant, indicate precision, only if there is a decimal point. Leading zeros are never significant. They are just placeholders. And with exact counts and conversion factors, we treat them as having an infinite number of significant trailing zeros. Here's some significant figure practice problems. Pause the video to work the problems. When you are done, restart the video to see the answers. Here are the answers. Pause the video so you can check to see if you are right. You are ready to learn about rounding significant figures.